Hi, my name's Dr. Barry Flannery. I'm the founder and CEO here at Xerotech. Welcome to another episode of XT Tech Talks. Today we're going to talk about the importance of thermal management and how it impacts battery packs. So let's get started. So we've already identified that heating and cooling of batteries is important. What we're going to talk about today is how you heat and cool a battery pack. One of the most important equations that governs battery pack design, or certainly the Xerotech battery pack design, is heat transfer. So there's a very important equation where basically the heat transfer is influenced by a number of main factors. So basically the mass flow rate times the heat capacity times the temperature difference. So what this means is that if you're flowing 1 liter a minute of water, and we'll just put to the side here that the heat capacity of water is 4,180 joules per kilogram per degree C. Kelvin, technically. This is a very important number in all cooling systems, and especially in battery systems when you look at other solutions that are available on the market today. So what this means is that if you take a liter of water, and 1 liter of water is equal to 1 kilogram of water, because its density is 1, you're basically multiplying these numbers out times the temperature difference of whatever that might be. So let's say the temperature of water entering and exiting a system. So if we're flowing water through something, let's say it's a heater element, and we have the water flowing in here at 1 kilogram a second, which is basically 1 liter a second. And the temperature when the water goes in at is at 50 degrees. And the temperature when it comes out at is at, let's call it 75 degrees. What we're able to tell from this is that the delta T, the temperature difference, is going to be 75 minus 50 equals 25 degrees Celsius. So we'd have a delta T here of 25 degrees. So what this means is, for our equation here, 4,180 joules per kilogram per degree Kelvin. And when we take this back, 1 joule per second is equal to 1 watt. And now we're back into power, energy, watt hours. So at this equation here, if you've got a kilogram a second or a liter a second of water flowing through something, and its temperature changes by 25 degrees C, you're basically ending up with 4,180 times 25, and let's work this out, what that number is, 104,500 joules. And if we were to divide this by 1,000, so that's joules per second, that's basically watts, that will be 104.5 kilowatts of heat generation. And this is an important thing to first start when you think about heat transfer and learning about cooling systems. Water is an incredibly unique substance for cooling anything or heating. That's why we run our power stations and everything else on them. The heat capacity of water is incredibly high, hugely high. And also other factors with water, when it vaporizes or turns to steam, is even higher again. So we're going to take a little deep dive into heat capacity, water, and what that means. If we say that 4,180 joules rises 1 kilogram of water by 1 degree C, what that means is if you had a kettle and you're making a cup of coffee or tea, let's imagine that that had 1 liter of water inside of it. So in our system, we have something with a liter of water, and we're heating this up. We would have to put in, roughly speaking, 4.1 kilowatts of heat to increase the temperature of this water by 1 degree a second. So let's imagine we're starting at 0 degrees C here. We will be heating up here 1 degree a second until we hit the boiling point of water, which is 100 degrees Celsius. So you would have to put in at this high heat rate. That's a very large amount of heat compared to other materials. So for example, metals like aluminium and copper and many others, they have much lower heat capacities in the sort of 300 to 1,000 range, and even lower than that in some cases. So water has 10 times more heat capacity than pretty much anything else out there. Even oils, like the ones that are used in battery cooling, like immersion cooling, has only about 2,000 joules per kilogram Kelvin. And other novel and unusual materials like dielectrics, like Novec and many other things, they have an even lower heat capacity. That's important because it means that when you're using them to cool something, they rise in temperature much more quickly than water. So water is very good at holding the temperature of something more constant. It stores much more energy inside of water as you try to heat it up. The other important thing when it comes to water is that when you want to go through something called a phase transition, so going from water at 100 degrees C to steam at 100 degrees C is totally different. So when you go through something called a phase transition, what you care about is the latent heat. And what this is, it's hidden energy you have to put in to the water to convert from water to steam at that same temperature. And what's important here is that for water, it is a massive number. It's a monumentally high number. So when we talk about the heat capacity of water being 4,180 joules, to change it from 1 degree Kelvin or 1 degree Celsius, to go from 100 degrees C water to 100 degrees C steam, there's a huge amount of energy. For 1 kilogram, it's about 2.2 million joules of energy. And where this becomes practically important in terms of maths is that's why we put out fires with water. It has a huge amount of heat capacity and heat quenching capability for the systems that we use it in today. What this would mean is that in our theoretical example here of heating up our 1 liter bottle of water with our 4 kilowatt element, which isn't far off most domestic kettles. Most domestic kettles are about 3 kilowatts. It will take from, say, a realistic case, room temperature, 25 degrees, and you want to bring this up to boiling point, 100 degrees C, that's 75 degrees of temperature difference, a delta T. That would take, let's say we had a 4 kilowatt element, 75 seconds. Takes about a minute. So if you wanted to go from 100 degrees water to 100 degrees steam in our theoretical kettle here, it would take 2.2 million divided by 4,180. This would be 526 seconds, a much longer time. So you'd be standing there for nearly 10 minutes waiting for that all to convert to steam, whereas it only took about a minute for it to boil to water at 100 degrees C. The reason this matters, and we'll talk about this in much more detail later on, for example in a Xerotech battery system, is it's integral to fire protection and fire safety. Using water as your fire prevention and safety mechanism is hugely important because it can suck so much energy out of a system to put out a fire, a flame, or to maintain the temperature of a battery system. So let's talk a little bit more about the practicalities of thermal management and using them in a battery. The common question is, do I need thermal management? How much thermal management do I need? And should I use this type versus that type? The first question is, it depends what you're trying to do. So with any battery system, thermal management will always make it better because the best thing you can do for a battery is to try and keep it in the 20 to 30 degrees Celsius range. A rough rule of thumb that applies to most chemistries is every 10 degrees C above 25 degrees C, battery life, as in cycle life, is reduced by half. So this is incredibly important. So even if you don't need to have your battery to be actively cooled down, so for example, you're discharging it very aggressively and you want to get maximum power out of it, that will generate a lot of heat. which has to be taken out of the battery so it doesn't have to shut down or be derated. Even in more mild applications, so these are batteries that have to operate for 8 hours a day or 10 hours or even 4 or 5 hours, it's really good to have thermal management, because if you can keep your battery at a nominal temperature, it's going to last a lot longer than a battery that has uncontrolled temperature. So thermal management is really important for day-to-day use cases to increase the lifetime of the battery and decrease the total cost of ownership. But also for high-performance battery systems, it's mandatory. If you're fast charging or doing aggressive discharging, you're going to be generating a lot of heat. So you have to get that heat out, and the only way to do that is with a thermal management system and probably some form of liquid thermal management system. And then you can get into the subset of, are there good and bad ways of doing liquid thermal management, be it direct or indirect? And that's usually a function of basically what's the pressure drop and then what's the temperature gradient. You want to try and minimize both. But in general, you want to maximize the heat transfer out of the battery, and you want to have the lowest temperature gradient. So you want your battery to be all at the same temperature and at the temperature that you want it to be. And that's some of the technologies that we employ help us do this better than most solutions available today. So in pretty much all battery systems, the way thermal management works is there's actually no thermal management happening inside of the battery. That's happening in an outside system. What we put in battery systems in the vast majority of commercial batteries on the market today is heat transfer systems. So even in a Xerotech battery, we can't control the temperature of the battery. That's done by an external system. So if you've got a module or a pack back here, that's got a coolant in and coolant out. What we give you inside of our batteries and every other battery supplier out there is a heat exchanger that's going to exchange heat between the battery cells and the cooling liquid. And depending on the design of that heat exchanger, there are good ones and not so good ones, depending on your flow rate and the temperature of that coolant. So the flow and the temperature. If you can put a high flow rate at a target temperature, you will get more heat in or out of a battery, and you will control its temperature much better. And that's when, as a battery pack designer, you're trying to optimize to have the best heat transfer coefficient and also the lowest pressure drop that's practical. So you want to maximize that heat transfer without having temperature gradients. There are different designs and more extreme cases here that you can have very high pressure drop systems that have much higher heat transfer coefficients. But the disadvantage of that is they result in very high temperature gradients. So to take the most extreme example, if you have a rocket engine nozzle that's shooting out huge amounts of energy out the back and heat, the rocket nozzle will melt. So actually what they do in rocket engines is they regeneratively cool the engine wall. So they basically flow the rocket fuel down the wall in tiny little microtubes that flows back again. So this does two things. It cools the rocket engine wall and recovers energy and increases the efficiency of the system. But this would be an example of incredibly high pressure drop systems. You need massive cooling pumps to do this. Thousands of horsepower of cooling things to drive that rocket fuel through those nozzles. But it results in extremely high heat transfer to deal with this. But the temperature gradients are also going to be very high. And the challenge with battery pack designs, and it's a problem even today, even some of the best engineers, the best pack manufacturers in the world have differing approaches to do this, and some are maybe good and some are not so good, is that you actually don't want to maximize heat transfer coefficients in a battery module because it results in massive temperature gradients. So if we had an extremely high heat transfer coefficient in our pack, what that would mean is if we sent in cold water here, this half of the pack is going to be freezing cold, and this half of the pack is going to be much hotter. So it's a balance. And this is when we're getting into real engineering. Everything is a trade-off in engineering. You have to find your design goals and optimize for the best things here. So every real battery system is usually a trade-off on many different factors. So as I said, in summary, no pack can control its own temperature. That is the result of an external system, which is basically a pump flowing water in the pack around in a loop. And if you want to get the heat out of the battery, flowing it in a loop like this won't get it out of the system. It's still going to be in that same system. You actually need another heat exchanger to get it out of the system or off the vehicle. And that's usually some sort of radiator that we're blowing air over. And that's ultimately how the heat gets out of the system. So overall battery thermal management systems have a number of different subsystems inside of them. Another heat exchanger that either raises or decreases the temperature of the system. In some cases, it might just be a heater. It's like having that kettle we spoke about earlier inside in the battery, where you just preheat it. And that's where some battery systems may have internal heating, is they use electric heating mats or an electric coolant heater. So when do we need battery thermal management? When's a good time to use it? When's it not needed? It's always nice to have, because it means you can keep at around room temperature. That's the goal. You want to try and keep a battery in a controlled temperature. It adds complexity, so some people might trade that off to eliminate that complexity, reduce cost, or there might be other considerations. But in some cases, it's mandatory. So in applications with high discharge rates, because you recall in previous videos, the fundamental equation of I squared R, so basically the more current that flows out of the battery cells, the more internal heating they generate. So if twice as much current is flowing out of the cell, it's generating about twice as much heat. So higher discharge rates, whether it's flowing into the battery, charging, or out of the battery, doesn't really make any difference. It's still largely dominated by this equation. So there's not a huge difference between charging and discharging of a battery pack from a heat generation perspective. There are some minor chemistry things that make it a little bit different, but fundamentally it's mostly the same. It's just about the rate. So if you're doing a 2C fast charge, you're going to need cooling. And the effectiveness of your cooling, the design of your heat exchanger inside of the pack will influence the temperature gradients within that pack, and overall will impact lifetime. So thermal management, you should always aim to try and do it to maximize lifetime. And if your battery lasts twice as long as the other battery, it'll be half the cost from a system perspective, depending on how you design it. But for high performance battery systems, supercars, fast charging, or some of the ones that are overlooked, hybrid applications, diesel electric hybrids in most systems that are coming in the next 5 years, they will definitely need thermal management, because these batteries are much smaller to handle peak loads. So they're usually operating at much higher discharge rates and C rates. So having highly effective thermal management is a critical enabler for hybrid battery systems. Let's talk more specifically about batteries, battery cells, and how we get the heat in and out. So for all practical battery systems, there's basically two main ways that they're cooled. You cool with convection and conduction. And in practical cases, it's usually a combination of both. So let's talk about a real cylindrical cell. So with your cylindrical cell, looking at it from the side here, or looking at it top down, if you have a bunch of cells together in a matrix, you can cool this a number of different ways. You can cool it directly. You could blow air directly over the cells. Air cooling is a relatively cheap, simple way of cooling batteries, but it's very ineffective. And the reason for that is the heat transfer capabilities of air are very low. The heat capacity of air is very low. So that's method number one, just blow air directly over the cells. If you blow cold air over it, it'll cool them down. If you blow hot air over it, it'll heat them up. The other one is liquid cooling. And let's take a similar example of direct liquid cooling. So air is an insulator. Air doesn't conduct in most cases electrically. So it's okay to blow air directly over cells, but this usually means your pack is going to be open to the outside air and the elements. There is methods of using direct liquid cooling, and this is sometimes called immersion cooling in the battery industry. What this is, instead of running air over the pack, you're running liquid directly over the cells in direct contact in some cases, by either flooding the whole pack or having small cooling jackets around the cells that then flow the dielectrics directly across them. This is a lot better. You benefit from the heat transfer capability of the liquid, but unfortunately most liquids are electrically conductive, for example water. So that generally rules out water for these types of systems. Instead, they use something called a dielectric. Basically means it doesn't conduct in most cases. The dielectrics, unfortunately, have a much lower heat transfer capability, usually about half, if not lower, than that of water, and have much worse thermal properties in terms of thermal conductivity and other factors. They're generally more viscous as well, which means it takes a lot more power to pump them. So that's directly cooling the battery cells. It can be an effective way, especially with direct immersion cooling or direct liquid cooling, but the challenges there are more practical of heavier solutions. Your dielectrics have lower thermal performance in some cases, and obviously leakages of the whole battery pack system because you have many more leak points in place. So the majority of the world do indirect liquid cooling. So instead of putting air or liquid directly over the cells, they basically do it through some form of heat exchanger. And the heat exchangers that are commonly used are almost always a cold plate, which is basically a metal plate that sits below the battery cells. And with these metal plates, because you can't directly touch the cell with the cold plate, they use something called a TIM, a thermal interface material. This is something that doesn't conduct electricity, but does conduct heat. Now, unfortunately, the laws of physics work against us here, that electrical conductivity and thermal conductivity are actually the same thing for the vast majority of materials. There's only a couple of very rare exceptions like diamonds and others where it doesn't rely on basically electrons moving is what carries the heat. And what this means in a practical sense is that metals are really good conductors of heat and they're really good conductors of electricity, whereas insulators are very poor conductors of electricity and unfortunately very poor conductors of heat. So for example, in a metal, let's say it was aluminium, its conductivity might be 300 joules per degree C, or watts per meter Kelvin, basically. If you're to go to a highly conductive thermal interface material, the best that exists in the world today, it's about 3, basically. So it's an order of magnitude drop in heat conductivity versus using direct metal on metal contact, but you can't use this. So that's what forces us to use these thermal interface materials. So that's what happens with our cold plate if we want to cool the bottom of a cylindrical cell. There is another approach where you can cool the side of the battery cell, like so. The big advantage of sidewall cooling is that there's more area. And where that's important is that heat transfer, especially for conduction, it's a function of area and temperature difference. So the more area you have and the bigger the temperature difference, the more heat that will flow between those two things. So cooling the side of the cell, because it's physically bigger in one dimension, more area. Theoretically, higher heat transfer. But you still have the same issue here with a thermal interface material. So either base plate cooling or sidewall. The vast majority of the market use base plate cooling because it's easier to implement practically. But more high performance systems, or most notably in Teslas and others, are achieved using sidewall cooling. Xerotech is a little bit different to the two of these. The vast majority of the market are using a metal heat transfer system, a duct, a pipe with little holes inside of it, where we basically pump the coolant through it. Xerotech, and what you can see beside me here is we use a very thin plastic duct. So in all of these cases, the metal has a very high heat transfer capability on the order of hundreds. The TIM is on the order of 1, 2, 3, or 4, because it comes down to the thickness of that insulator. Thin insulator, higher heat will flow through it, higher heat transfer flows through it. Xerotech, we basically eliminate the metal entirely. And you can imagine our ultra thin polymer plastic duct, plastic so it's an insulator naturally, is actually better than this, because what we do here is we're able to thin down that TIM to as small as it can possibly be, and also we're able to maximize the contact area on a battery cell because the duct expands and inflates around the battery cells. So you basically get perfect angular contact around the battery cells. This is a big problem, for example, in the early Tesla Model S days, to try and get an extruded aluminium duct in between the cells and have a squishy rubber thermal interface material to contact the cells. So if you've got a cooling system that can inflate and fill all of the space perfectly, ensuring perfect contact area, also being extremely thin, you end up with a very good cooling system. So when we get back to the fundamentals of putting the heat in or taking the heat out of a battery cell, it's a function of area that you're touching, temperature difference, and conductivity or resistance. So by maximizing the area, and another thing you can do is increasing the temperature difference, so run cold water through your cooling tubes will increase the heat transfer, and then decrease the thermal resistance between your water and what you're trying to cool. That maximizes heat transfer. So we're going to go into some specific details now of the considerations of real engineering, battery pack engineering, and actual practical stuff, now that we have a little bit of an understanding of the laws of physics here. One of the other factors you have to worry about when you're designing your battery pack is actually flowing the water through that heat exchanger. The vast majority of them are extruded aluminium heat exchangers, meaning that there's little holes in here that they're pumping water through. And another law of physics to do with pumps is that you need a force, you need pressure to pump water through something. And that means that as we flow through from one end of a pipe to another, I need it to be higher pressure on this side than here, because the water has to flow across it. And that means that you get something called pressure drop. You lose pressure, you lose energy. It takes power to pump water through something. But what's important is that that pressure drop equation is very non-linear. It actually goes up to the power of 5, the diameter to the power of 5. So that means that if you had a pipe and you made it half as small or half the diameter, the pressure drop overall, due to an equation called the Darcy-Weisbach equation, will go up by a factor of 32 times. So what this means is that having small openings in your cooling systems can result in huge, huge pressure drops. And at the end of the day, what that means is we can't get as much water through the cooling system. And you might recall our early equation here, where the heat transfer is the mass flow rate times the heat capacity times the temperature difference. So if you're trying to get some heat transfer through the system, you're not going to change the liquid. It's always going to be water, so this never changes. So the only other thing you can change is the temperature difference, or in some cases, the mass flow rate. And in the case of a battery pack, you want it to be even temperature. So with this battery module in front of us here, you want the cells at the start of the module to be as close as possible to the temperature of the cells at the end of the module. So now what we're talking about here is actually the delta T. So if you imagine in our pipe, let's go away from pressure drop and now look at heat transfer. So let's say we're taking heat into the water, i.e. we're cooling down these battery cells. That means there's heat going into the water as it flows through this heat exchanger. That means that the water at the start is going to be colder. For example, it's at 20 degrees C, but as it goes through the pipe, it's getting warmer and warmer and warmer until it comes out the far end. And depending on the flow rate, the mass flow rate here, this temperature gradient could be 30 degrees C. And that can be a big problem in battery packs, because when we say the battery is at a certain temperature, we want it to be uniform. We want to have a uniform temperature distribution across that battery module. So the only way that you can reduce this temperature difference between here and here is to change this equation. You have to make this number bigger. If you want this heat transfer to be the same, 1000 watts or whatever it might be, it's a zero-sum game. This has to get bigger if you want this to get smaller. And in battery packs, you want your delta T, your temperature difference, in this case here, or your gradient, which will be a function of this. So your cooling liquid temperature gradient will influence your module temperature gradient. This is very important. You want this to be as low as possible, and you want this to be as high as possible. The problem with most battery pack designs on the market today is they're all using heat exchangers with small little openings like cold plates, like other sidewall multi-lumen extrusions. So remember the equation I wrote down, this Darcy-Weisbach equation. One of the key terms in that is to the power of 5. And what it actually ends up meaning is that when we talk about pressure drop as a function of flow rate, it's an exponential. It goes crazy. So that means that, okay, I want to get my temperature gradient as low as possible in my battery, increase the flow rate, put on a bigger pump. The problem is that you're fighting an ocean, basically. The more you pump, the higher the pressure drop, the more energy you need. It becomes exponential. So it's not quite you need twice as much flow rate, you need 4 times as much power. It's even higher than that. It's exponentially higher as you go up. So it's incredibly important to design your systems to have a low pressure drop. That's what's one of the unique and, I guess, innovative aspects of what we do at Xerotech, is that it's a completely open structure. So when we sidewall cool our batteries, it's just a fully open pipe. There's no little holes and ribs and extrusions or anything, just it's a completely open structure. So the pressure drops, and you'll see this in our data sheets and our catalogs, they're an order of magnitude lower than what everyone else in the market has. And where that's really exciting is it means that we can have an order of magnitude higher flow rate through our modules, through our packs than anybody else, which means our temperature gradients are much lower. Our heat transfer is much higher in that case. So this is really, really important for controlling the temperature of battery modules. So if we're to recap now, controlling the temperature matters because if your battery gets too hot, you may have to shut it down or reduce the amount of power that comes out of it. Similarly, as we've discussed in previous videos, if it's too cold, you can't use it at all. You can't recharge the batteries. And in some cases, they even cease to work altogether at -40 for some chemistries. So heating things up, cooling them down is very important. And there's a lot of different ways to do that. There are good ways and there are better ways. And then there are some not so good ways. So we did speak about 3 main types of cooling: air cooling, direct liquid cooling, and indirect liquid cooling. There are a couple of other more exotic solutions, but they're not very prevalent on the market out there. You've got something called phase change systems, and then you'll also have refrigerant, which are a combination of these. So basically the phase change systems rely on that latent heat that we spoke about before, where for the example of water, it would go up like this, stay flat for a very long time before it heats in temperature again as you go through this phase transition. This phase transition for water happens at 100 degrees C. That's not good for battery cells. That's extremely damaging to battery cells to be at that temperature. But there are other materials, for example, waxes, paraffin, and things like that, that you can actually engineer that phase change to happen at a lower temperature, a useful temperature. For example, 20 or 30 degrees Celsius. So that's a passive way of cooling batteries that requires no moving parts in most cases. The problem with some of these phase change approaches is that it's only a storage method. It doesn't actually cool the battery, it just delays it heating up. And then you have to recharge that phase change by basically sucking the heat out. So it basically acts as a big buffer tank. Refrigerant systems are quite similar to direct liquid cooling, except as opposed to staying in this region here, they actually make use of the phase transition. They actually rely on the refrigerant vaporizing, causing large levels of cooling, or condensing in the other case. The challenge with refrigerant or phase change, vapor change systems is that it generally results in a much higher pressure buildup, a very different design of the battery module. You're effectively designing your battery to be inside of a refrigerant cooling system. So the system challenges are quite a bit higher for some of the performance that you get from it. And even still, it's very hard to beat water in most conventional systems. So what are some other considerations of how you cool a battery cell? There's a bit of a debate out there in the engineering world of whether it's best to cool the bottom of a cell or to cool the side of the cell. And the reason for this is that the heat transfer into the cell, it's very different depending on the direction. It's something called anisotropic. It's not the same in both ways. And the reason for that is inside of the battery cell, it's basically a spiral wind of anode, cathode, and separator. So basically plus, minus, and something to stop plus and minus from touching. That separator, remember what we spoke about earlier, an insulator, is not electrically conductive, which means it's not thermally conductive. So that exists in between each of these layers. So while the anode and cathode and electrodes are very conductive, it's basically going from very conductive, not conductive, very conductive, not conductive, very conductive, not conductive. So that means that when you cool the battery cell wall with your heat exchanger, the theory is that it's not as good to cool from the side as from the bottom, because at the bottom of this, you've basically got very conductive, very conductive, very conductive, very conductive, very conductive, and so forth here, as well as the insulators. So you'll get higher heat transfer up through the battery cells. There is some logic and rationale to that, but in all real applications, and from my own personal perspective, any high performance battery system I've ever seen across all suppliers, it's usually either a combination of cold plate and sidewall cooling or exclusively sidewall cooling, because you have to remember that in practical situations, cooling the sidewall, it also conducts down and cools the base of the can as well. So sidewall cooling tends to dominate higher heat transfer overall. It can in some cases lead to temperature gradients across the cell as you start to get to higher and higher levels of heat dissipation or heat exchange being required. So if you're cooling down here with something very cold, it's not able to conduct the heat down here very well. But it's even worse in a sidewall situation. What actually ends up happening is the middle of the cell can be quite hot, and then it's getting colder and colder as you get to the side until you get to the side wall out here. So you actually, it's not even a temperature gradient across the module, it's a temperature gradient across the cell. This is a very important design characteristic in ultra high performance battery systems like hypercars, VTOLs, and many other things. So they all matter. But in practical considerations for cylindrical cells, it doesn't make a huge difference from what we've seen. We prefer sidewall for a number of different reasons. One of the big advantages, it can simplify your bus bar connections to not have to deal with it here. And it also helps when you're using it for thermal propagation, prevention, and other passive safety features like what we use in our battery systems. The other thing to point out is when it comes to heat transfer is the cell size and cell format does make a big difference. In the same way we spoke about here, the electrically insulating factors, the size of the cell matters. So if you use a bigger cell, say you go from 2170 to 4680, your problems get worse because this heat transfer path becomes longer. And you don't really want that because it means that you're getting higher and higher resistance from your core, so you can't get the heat out as easily. So those of you might have in the industry would have heard of tabless battery cells, an invention with Tesla and many others have deployed this. What they're trying to do there is decrease the thermal resistance at the bottom of the cell to promote the heat transfer out of it, to make them more effective for sidewall cooling. But even still, an important fact that I point out even to my own engineers is that when you take the Tesla 4680 tabless design, they're still doing sidewall cooling. Now that might be for manufacturing reasons as opposed to performance reasons, but it's an interesting point nonetheless. When you consider large format cells, we're talking very large prismatics, you can quickly see that the heat transfer on a cold plate can present real problems here, that it's very hard to get the heat out of these cells. That's why we believe at Xerotech in having small units of energy, physically small, because you can control the temperature a lot easier, even ignoring all of the safety factors that go into it. So to summarize on thermal management as a whole, do you need it? Yes, it's a nice thing to have. In some cases you can do without it, but it will come at the expense of life unless you've got a very particular application that's been engineered. So thermal management's always a good thing. Important to point out that very few packs have thermal management in them. What they have is heat exchangers. Heat exchangers get the heat in and out of the pack. A thermal management system like a heat pump, an electric coolant heater, a radiator is all outside of the white box, somewhere else in the system. So that's separate to the battery packs, as is the pumps. So this gives you a super highway in and out of the pack or in and out of the module, but it's up to the end users typically to get it off their vehicles or out of their systems. Thermal management, incredibly important for a lot of future applications, especially hybrids, which are going to be a big thing for heavy duty industrial vehicles that are going diesel electric, as well as full BEV, and also high performance vehicles that generate a lot of heat. You must have strong thermal management for these, or it can result in a safety risk, because if you keep discharging on these cells, their temperature will just keep climbing. And if it reaches a certain threshold for some chemistries, they can go on fire. So thermal management, very important to maintain the safety of the battery. But also you can't forget the outside world. It can get quite hot outside. That can result in a derating of the battery's performance. So that concludes our little deep dive into thermal management systems, but from a more practical battery pack engineering perspective. So I hope you found that insightful, and thanks for watching.